When we talk about the derivative, it tells us, it's describing the actual shape of the function itself. So here is an extremely important two sentences that we see in calculus. If the derivative is positive on an interval, then the function is increasing on that interval. If the derivative is negative on that interval, then the function is decreasing on that interval. We have to make sure that we know this. And we have to make sure that we have that down. So we have to memorize that and understand that connection between the derivative and the original function itself. We also can then, you can also say, well, if you know when it's increasing and decreasing, and there's a change from increasing to decreasing, then that's where you're going to have a maximum. Decreasing and increasing, a minimum. And those are some other things we'll talk about. Concavity. This reinforces the idea of when something's concave up and when something's concave down. If the second derivative is positive, that's concave up. If the second derivative is negative, then the function's concave down. These two definitions, these two sentences, we must know inside and out as well. Here's an example. This function's always concave up. So what can I say about the second derivative here? It's positive. This graph is concave down. So what can I say about the second derivative? It's negative. The second derivative will describe the shape of the curve, either concave up or concave down. And this is something that we'll see again and again in the beginning part of calculus here. Okay, here's an idea that kind of puts these topics together into one problem. It says, this will be a big, try to sketch the graph of a function that meets the following criteria. So we have three criteria that we need to use to graph this function. So the first thing we need to do is we need to say f prime of x is positive on the interval from -1 or negative infinity to 1. What does this piece of information tell us? What does the function have to be doing if the derivative is positive? It's got to be increasing. Okay? And the derivative has to be negative from 1 to infinity. So what has to be happening from 1 to infinity? It has to be decreasing. So it's so what we could do, just to summarize that a little bit, we can make a little f prime line. And before 1, we know it has to be positive, so it's increasing, and negative, so it's decreasing. This tells me what the graph is doing before 1 and after 1. So that's the first piece of information that they give us. The second piece of information is the second derivative. So the second derivative from negative infinity to -2, the second derivative is positive. So what do I know about the graph? Concave up. Concave up. And then, from 2 to infinity, it's concave up. And then it's negative between -2 and 2. So that means it's concave down. So if we want to kind of summarize that a little bit with an f double prime line, we can make an f double prime, which is second derivative. We can go to -2 and then 2. And then we know that it's going to be it's positive and then positive and negative. So it's going to be concave up, concave down, and concave up. So there's the concavity of the graph that we see when we're trying to sketch this function itself. So the third piece of information talks about the limits. Okay? The first one's the limit as x goes to negative infinity equals -2. What does that tell us on the graph? When you take x and you go to negative infinity, what's that giving us on the graph? Which asymptote? Horizontal. It's a horizontal. Because x is going to negative infinity. So x goes really small. Where's the function value going? It's -2. So there's going to be a horizontal asymptote at y equals -2. And then this other one says the limit as x goes to positive infinity is going to be 0. What does that tell me? There's another horizontal asymptote at y equals 0. Now remember, the one at 0 is going to be approached when we go to positive infinity, and the one that is at negative 2 will be approached when we go to negative infinity. So now we put this all together. We put it together in a graph. What I would do is I'd probably sketch in the asymptotes. So I know that there's a horizontal asymptote at negative 2. So I put down a dotted line at y equals a negative 2. I also do the same at 0. Y equals 0. The other thing then that I know is that this graph has to be, it's increasing up to 1, and then it's decreasing after 1. So what happens somewhere at 1? Like right there. I don't know where that's at, but I'm just going to put it right there. What does that appear would be on the graph if we change from increasing to decreasing? Increasing to decreasing, a max. Yeah, it's a max. It's a vertex. It could be a vertex. At this point, it appears to be a max value. So this could be like the top of the graph. And then we know that the graph is going to be increasing up to that point. It's got to be increasing and concave up to negative 2. So up to negative 2, we've got to be increasing concave up like this. See, it looks like it's kind of concave up. And then we still got to keep increasing, but now we switch the concavity so it's concave down. So now it looks kind of like it's going concave down, but it's still increasing up to that point. Now, after 1, we're going to be decreasing, but we're concave down up to 2, because that's what this piece says, concave down from negative 2 to 2. So going to negative 2, still concave down, and then it switches to be concave up and go like this. Okay, a couple things we got to fix here is the fact that, first of all, the labeling up here, that should be, the 2 should just be 1 over a little bit. So let's change this so that that would be a 2. So I have this as a 2 here. And we're going down to 2. Now we changed the concavity, but we had to remember, I forgot about the horizontal asymptote at 0. So because it's at 0, that says x goes to infinity, I changed my concavity, so it's going concave up, but then it's going to approach 0 as we go to infinity. So there we see that it's concave up, approaching infinity to the right. We would appear that there's going to be an inflection point at 2 and then at negative 2. Those would be called inflection points because the concavity changes on the graph itself. This is how it all ties together. All those characteristics tie together to be able to describe the actual graph itself. Questions? The one thing on the bottom, just to address it a little bit, they talk about what an antiderivative is. If we can find a derivative, certainly we can undo it or go backwards. An antiderivative of a function is usually written with a capital F with the requirements that the derivative of the antiderivative is the original function. Okay, let me just we're going to be talking, this doesn't come up until later on in calculus where we start talking about the antiderivatives, but basically the idea is this. If the function itself, let's say is 2x, this is the function itself, the derivative we're going to find out is going to be 2. And I'll just tell you that with magic this happens, but that's the derivative. And if we were going to look at the antiderivative is going to be an x squared plus something. Could be a plus c. but there is a function that goes backwards that really is going to be a way to undo the derivative. So the derivative of x squared is going to be 2x. And this is something we're going to go on talking about later. Don't worry about this right now. But it was on here, so I wanted to address it. Last one that we have has, given this graph, which of the following is true? So here's a graph of a function, and this is actually an AP problem that was on a multiple choice exam in the past. And they're just asking you to say which one is true. So what we need to do is we need to examine the function at 2. We need to look at the functional value. We need to look at the derivative. And we need to look at the first and the second derivative value. So first of all, f of 2. What does f of 2 equal? 0. That's simply the functional value. That's all that is. Now let's look at f prime at 2. What does the first derivative at 2 tell us? The slope of the tangent line. So I draw the tangent line here, and I look at this slope. What do I know about that slope? It's negative. That might be enough. So I'm just going to say slope is negative at 2. Okay? If it really came down to it, I could maybe estimate that to be about -1. But I'm going to just say slope is negative for right now at 2. The third thing we're going to look at is the second derivative. What does the second derivative tell us about the function? Concavity. When you look at this graph, does it look like a cup going up or a cup going down? Up. So it's concave up. Concave up. So what does that tell us about the second derivative at 2? It's positive. Okay, now we just organize this together. We put the smallest one first. So what's the smallest one out of these three? F prime at 2. So F prime at 2 has to be first. Then what's a little bit bigger than that? F of 2, because that's 0. And then the next one would be F double prime at 2. So this is the correct order that we're looking for. Then we'd be very careful when we select the answer, because they all look the same. I mean, it's standing back, 10 feet or so, you wouldn't know which one is which. But you look at it a little closer, and then you can see, well, I got an F prime at 2, and then I have F of 2, and F double prime at 2. So it looks like it's going to be C, as long as you had it all in the correct order. But it's really, really easy to select the wrong answer, even though you got the right answer. I see it all the time. So be very careful about that. But this is a big thing to get down with the derivative and the first and second derivatives.